Hello, my name is Kolzi Suga, and I'm going to talk about model training, evaluation, and optimization for our project, which is acoustic phenotyping for early detection of aviation respiratory diseases. This is the content of the presentation, and straight away, I'm going to first talk about the background and introduction. Respiratory diseases in poultry, like infectious bronchitis or Newcastle disease, spread rapidly in poultry farms, leading to high mortality rates and massive economic losses. The manual monitoring by farmers is labor intensive, subjective, and often identifies illnesses too late for effective intervention. Chickens with respiratory distress produce distinct sounds that differ mathematically from healthy vocalizations. So the early detection can reduce the need for mass and antibiotics and prevent total frog growth. Uh, AI-driven early detection of respiratory diseases in poultry via audio analysis is a project aimed to develop a non-invasive real-time monitoring system that uses machine learning to distinguish between healthy, unhealthy, and ambient noise. Utilizing digital signal processing to extract acoustic features like MFCC and spectral centroids for classification and providing an automatic early warning system that operates 24/7, ensuring better animal welfare and biosecurity. Then the problem statements, I'm going to start with the domain application problem. The poultry industry faces critical vulnerability in rapid undetected spread of respiratory infections such as infectious bronchitis and Newcastle disease, which can which can devastate entire flocks within days. Current monitoring relies heavily on manual human inspection, a process that is not only labor intensive and subjective, but often fails to identify illness until birds reach a clinical tipping point, where intervention is too late. Furthermore, the necessity for constant physical presence by the farm workers increases biosecurity risks through potential cross-contamination. This delay in diagnosis leads to massive economic losses, high mortality rates, and an increased reliance on broad spectrum antibiotics, highlighting an urgent need for non-invasive 24/7 automated health monitoring solutions. Then for our computational problems, or how we're going to use computer to solve the problem, from the technical perspective, developing an automated audio-based detection system is complicated by the high decibel, chaotic acoustic environment of a modern poultry house. The primary computation challenge lies effectively isolating the subtle, impulsive sneak or rel of the sick chicken from dominant background interferences such as ventilation fans, mechanical feeders, and the communal noise of thousands of healthy birds. Additionally, the non-stationary and sporadic nature of chicken vocalization requires the extraction of highly specific robust acoustic features like MFCC and spectrocentroids that can maintain high classification accuracy across different farm acoustics. Finally, there is a significant engineering hurdle in designing a model efficient enough to perform real-time analysis at the edge without requiring high latency cloud processing. Then these are some of our research questions and objectives. How can healthy chicken vocalization be mathematically distinguished from those affected by respiratory distress in a noisy farm environment? Which acoustic features provide the highest sensitivity for detecting early stage illness? Another question can be, Can a machine learning model maintain high accuracy while ignoring non-biological ambient noise from fans and feeders? Some of our specific objectives for the audience, these are the some of the objectives. To extract and analyze discriminating acoustic features from chicken audio to identify unique disease signatures. To develop a robust machine learning classification model capable of categorizing audio clips into healthy, unhealthy, and noise classes with high precision. Develop the performance and accuracy of a model using validation metrics to ensure reliable early stage detection of respiratory distress. To design a framework for real-time monitoring that minimizes the impact of ambient farm noise on diagnostic results. So this is my methodology and the system architecture. I managed to build two models, one for the MFCC model and the CNN spectrogram architecture. This is the flow of each of the models. For the MFCC model architecture, we first capture the audio from the poultry, then it goes under pre-emphasis, then framing, windowing, fast Fourier transform, then we frequency wrapping spectrum, then we extract the MFCC features, then the CNN Mel-Spectrogram architecture, that's the flow. Then this is my model evaluation. Model evaluation where I managed to capture the precision, the recall, F1 score, and the support of the two models. You have the healthy precision, the healthy recall, healthy F1 score, and the support, and the other classes that we managed to capture for the different classes of the audios. Then the accuracy of the first model was 0.8. That's the accuracy score I managed to get. Then when you go to the CNN model, also you capture the precision, F1 score, recall, and the support. Then its accuracy was slightly below the MFCC model, because the accuracy of CNN I managed to get 79%. I also managed to capture the macro average. Then we have the weighted average for the sounds or the audios that we used in our data set. Then next, I'm going to talk about how each of the models works and how do they learn. I'm going to start with the MFCC model. The audio recordings are first processed using the male frequency capture coefficients extraction, which converts the sound signals into compact set of coefficients that present the spectral characteristics of the audio in the way that approximates how sound frequencies are perceived. This process involves filtering the frequency spectrum through Mel-scale filters at different stages, then taking the algorithmic energies and applying a discrete cosine transform to produce the feature matrix capturing the dominant frequency patterns of the sound. These MFCC features are then fed into a neural network like dense classifier which learns to distinguish patterns in coefficients that correspond to health and unhealthy chicken vocalizations. The model learns by iteratively adjusting the internal parameters during the training to reduce the prediction error between its outputs and the true labels. Through this optimization process, The model gradually identifies distinctive spectral signatures associated with different poultry health conditions, allowing it to classify new audio samples accurately. So briefly, I'm explaining the flow of the architecture of the MFCC model. And then when you go to the CNN Mel-Spectrogram model, we first capture the raw chicken audio recordings. So these recordings are first converted into spectrograms, which represent how sound energy is distributed across frequencies over time. This transformation converts the audio signals into an image-like representation, where the horizontal axis represents the time and the vertical axis represents the frequency, and the color intensity represents the signal energy. The convolutional neural network, or the CNN, processes this spectrogram by applying multiple convolutional filters that scan the input to detect meaningful acoustic patterns, i.e., frequency bursts, vocal rhythms, and spectral shapes that may indicate health or unhealth chicken sounds. As the signal moves through deeper convolution and pooling layers, the model progressively learns more complex patterns and relationships within the sound features. During training, the models learn by comparing its predictions with the true labels, that is health, unhealth, and noise, and minimizing the classification error using loss function optimized by algorithms such as ADAM through backpropagation. Over many training iterations, the network adjusts its weights to improve its ability to recognize subtle acoustic differences associated with the poultry health conditions. So this is the flow and the architecture of the CNN spectrogram model. Then we'll talk about the AI techniques used to audit the models, or these are techniques used to minimize the errors in our models. Number one, I talked about the confusion matrix. Model auditing was conducted using confusion matrix and the classification metrics such as precision, recall, and F1 score, as I portrayed up in the previous slides on the model evaluation. These metrics helped identify patterns of misclassification, e.g., whether environmental noise can be confused with unheard sounds. This analysis ensures the model performs reliably across different classes of audio. Then another technique was feature importance analysis. For the MFCC-based model, feature importance analysis was used to determine which MFCC coefficient contributed most to the classification performance. Then by analyzing the influence of individual features on predictions, I identified which frequency components of chicken vocalizations were most relevant to distinguishing healthy and unhealthy sounds. Then another technique was GRAL-CAM, which is the gradient weighted class activation mapping. This was applied in the convolutional layers of the CNN models to generate heat maps showing which parts of the spectrogram contributed most to the classification decision. The technique uses the gradients flowing into the final convolutional layer to produce a visual explanation to highlight the most influential time frequency regions. This allowed me to confirm that the model was detecting meaningful sound patterns related to poultry vocalizations in the audio datasets. Then the last but not least, silence maps. These were used to highlight the regions of the spectrogram or MFCC feature map that most influenced the model prediction. By computing the gradient of the output with respect to the input features, the method identifies the time frequency regions that the CNA considered important for classifying a sound as health or unhealth. This helps verify that the model focuses on relevant acoustic signals, i.e. vocal intensity, rather than background noise. Then the dataset description and exploratory data analysis. The dataset that I used, it's called Chicken Audio Dataset. It's a specialized library of 364 audio recordings designed to facilitate the detection of aviation respiratory issues. The dataset is balanced across three critical categories. For health, we have 139 samples, and unhealth, we have 121 samples to provide the biological contrast needed for diagnosis. And we also have the noise samples, which are 86 samples, train the model to ignore environmental interference. Each sample was processed as a .wav, or that is the extension of our files, audios in the dataset, and standardized to a duration of 3 seconds. This uniformity ensures that extracted acoustic features such as MFCC and spectrocentroids are comparable across the entire dataset, allowing the AI to focus purely on the acoustic signature of the birds, health, or rather than recording variances. So the EDA results, graphs, and insights. The exploratory data analysis, or the EDA, successfully validated the acoustic differences between the three classes. Time domain waves revealed that healthy birds produce sharp impulsive bursts, whereas unhealthy birds exhibit continuous low amplitude jagged waves indicative of labored breathing. Then the frequency domain analysis through spectrograms further highlighted that respiratory infections causes spectral smearing, replacing the harmonic bands with broadband noise. Statistical distributions of spectrocentroids confirmed that unhealthy sounds are significantly brighter or harsher than the healthy ones. Then finally, the TSNE vocalization served as the most critical insight, demonstrating that combined MFCC and chronicle features form distinct non-overlapping clusters. This clear separation provides strong evidence that a machine learning model can accurately automate the detection of respiratory diseases in a real-world environment. These are some of the outputs, results, and the discussions of our AD visualizations. The first diagram is showing the amplitude of the waves produced by the sounds. The one in blue is for the healthy chicken, or the audio sounds produced by the healthy chicken. The middle one for the noise. Then the last one in red is for the unhealthy chicken. I see that these ones, the waves, or the amplitude of the waves, helps us to easily identify or distinguish between different sounds. Then the next image shows the spectrogram frequency of the audio clips produced by the three categories, that is health, noise, and unhealthy chicken. Then also we managed to capture the zero crossing rate comparison of the different audio groups. Then the loudness profile of the birds, then spectrocentroid, or the frequency center, and others. Yeah, that was my presentation.